In the fall of 1957, the Soviet Union placed the first artificial satellite into orbit. The successful launch of Sputnik placed immense political pressure on the United States to prove it could compete in a rapidly escalating Cold War. The American response was Vanguard TV3. Broadcast live to an anxious public, the rocket ignited, lifted a mere 4 feet off the launch pad, lost thrust, and collapsed back to Earth in a massive explosion. The failure played out on the global stage. Newspapers openly mocked the disaster, dubbing the American effort Kaputnik and Flopnik. The surviving satellite was thrown clear of the wreckage, transmitting a signal from the dirt while the rocket burned. This highly visible humiliation exposed the fragmented, disjointed nature of the various United States military space projects. Realizing a divided effort could not compete, the government consolidated aerospace research into a single civilian agency. Less than a year later, NASA was formed. 10 years later, NASA was preparing to land humans on the moon. On January 27, 1967, astronauts Gus Grissom, Ed White, and Roger Chaffee entered the Apollo 1 command module for a routine pre-flight rehearsal. The rocket was completely unfueled. However, the cabin was pressurized with a pure oxygen atmosphere. A microscopic electrical spark from exposed wiring ignited the highly flammable materials inside the cabin. Fed by the pure oxygen, the fire spread rapidly. The crew attempted to escape, but the interior hatch was designed to open inward. The rising pressure sealed it shut, trapping the astronauts inside. All 3 men perished. NASA immediately suspended the lunar program to dismantle the module and trace the fatal flaws. Engineers stripped out combustible materials, overhauled the electrical wiring, and redesigned the hatch so it could open outward in seconds. The tragedy grounded NASA for nearly 2 years. The capsule that eventually carried the Apollo 11 crew safely to the lunar surface and back was heavily modified as a direct consequence of the physical design oversights discovered in Apollo 1. By the 1980s, the Space Shuttle program was in full swing. To secure continuous funding, NASA presented the shuttle as an operational, highly reliable vehicle, a safe commuter ship that would make access to low Earth orbit routine. On the unusually cold morning of January 28, 1986, the Space Shuttle Challenger launched. Engineers from the contractor, Morton Thiokol, explicitly pleaded to delay the flight, warning that the freezing temperatures would compromise the solid rocket booster seals. This page from the Rogers Commission report identifies the exact mechanical failure. The investigation concluded the destruction of the O-ring seals allowed hot combustion gases to leak, severing the structural attachment and resulting in the loss of the vehicle 73 seconds into the flight. 17 years later, the agency repeated a similar organizational error. During the liftoff of Space Shuttle Columbia in January 2003, a suitcase-sized piece of insulating foam broke off the external fuel tank and struck the leading edge of the left wing at incredible speed. This map details the ultimate result of that impact. While Columbia was in orbit, lower-level engineers requested military satellite imagery to inspect the wing for damage. Program managers, relying on past missions where foam strikes hadn't caused lethal damage, denied the requests. During re-entry, superheated plasma entered the compromised wing, tearing the shuttle apart. Both disasters were symptoms of the normalization of deviance, an organizational culture where operating outside of safe design limits becomes acceptable over time simply because previous flights survived. The hardware failed, but the root cause was a management system that prioritized launch schedules over engineering reality. Physics does not respect deadlines. In the late 1990s, NASA adopted a faster, better, cheaper philosophy for its uncrewed missions. Under this aggressive framework, the Mars Climate Orbiter launched on a 10-month journey to study Mars. This chart illustrates the discrepancy that doomed the mission. Ground software was coded using imperial pound force, while trajectory modelers assumed metric newtons. This introduced tiny errors. Reaching Mars, its trajectory was 170 kilometers too low, plunging the $327 million spacecraft into the atmosphere. Just months later, the Mars Polar Lander disappeared during its descent. Investigators determined that a small vibration as the landing legs unfolded tricked the onboard software into sensing a touchdown, shutting off the descent engines while the craft was still high above the surface. In deep space operations, the margins for error are virtually non-existent. A misplaced unit of measurement or an unverified line of code will cause highly sophisticated hardware to vanish into the void. In 2001, the Genesis mission launched with an ambitious objective: travel into deep space, collect pristine solar wind samples, and return them to Earth. The plan called for the sample return capsule to deploy parachutes so it could be safely snagged midair by helicopters. When the capsule re-entered the atmosphere over the Utah desert in 2004, the parachutes never fired. The vehicle tumbled violently out of control, slamming into the ground at hundreds of miles per hour and cracking open the delicate payload. The Mishap Investigation Board identified a severe physical error inside the avionics unit. The microscopic gravity switches, designed to sense atmospheric deceleration and trigger the parachutes, had been installed completely upside down. This inverted installation slipped past quality control because the switch circuitry was classified as a heritage design, a component that had worked successfully on previous missions. Trusting its pedigree, project managers decided to skip standard centrifuge testing to save time. The Genesis crash demonstrated a crucial vulnerability. Assuming a part is safe simply because an older version worked in the past leads to blind spots. Every system requires rigorous physical verification, regardless of its legacy. Examining these missions reveals a clear pattern. The vast, freezing expanse of the universe is intensely hostile, but the flaws that destroy spacecraft are invariably earthly. Rigid schedule pressure, untested assumptions, and poor communication break rockets long before the vacuum of space does. Yet, NASA's history is defined by its capacity to adapt after these devastations. The humiliation of Vanguard consolidated the infrastructure needed to reach orbit. The ashes of Apollo 1 dictated the rigorous design protocols that successfully carried humans to the moon. Today, the extreme vigilance governing modern programs, like the Artemis lunar missions, is a direct inheritance. Their safety margins, independent oversight boards, and extensive testing procedures were forged by the tragic losses of Challenger, Columbia, and the Mars probes. Pushing the boundaries of human reach guarantees that failures will happen. The measure of a space program is not the absence of mistakes, but the humility to study those failures, correct the culture, and launch again.